Okay, now this is a cool problem, and there's going to be some interesting features here, and it's going to make us solve a system of differential equations. So there's going to be a lot going on for this problem, and again, I think it's just a really interesting problem. Okay, so to begin with, let's look at this Cauchy data here. So the Cauchy data, u of xy is equal to f of x for x greater than 0. So we're only looking at the right half of the plane. So let me just go on ahead. This will be the y-axis. Oh man, didn't mean to stop. So with the bamboo tablet, like this is not, hopefully, things will be working a little bit better tomorrow or next week for y'all. Okay, and then I don't want that there. And then this will be the x-axis, of course. Not quite on the line, but whatever. I'm not going to change anything at this point. Oh. Okay. So this is the x-axis. This is the y-axis. Okay, again, x dot of s, this is minus y, because that's what's multiplying the x derivative of u. And now x of 0, which is going to be a generic point on the x-axis, the positive x-axis, because we only care about x greater than 0, so that's going to be x naught. Y dot of 0 is equal to x, and y of 0 is going to be equal to 0. And this is z dot. Remember, this is always z dot, or sorry, yeah, this is always z dot of s. And notice it's equal to u, which is just along the characteristics is just equal to z. So z dot of s is equal to z of s. Z of 0 is equal to u of x naught. Y naught, which in this case is just going to be f of x naught. Okay, now before going about solving this system of differential equations, I just want to talk about this vector field. So the vector field for the characteristics the velocity vector, the tangent vector field for the characteristic equations, these are given by minus y is the first component, and x is the second component. Now, my guess is that you've seen this vector field. This is kind of a popular vector field to talk about in like a vector calculus class, because what's happening here, if I consider a circle, so just draw what these vectors are going to look like at different points on the x and y axis. But notice, if I look at the parameterization of a circle, so if I look at the parameterization of a circle, it's going to be r cosine theta, r sine theta. Okay, and if I take the derivative of this with respect to theta, in other words, if I find the tangent vector, I'm going to get r minus r sine theta, and then r cosine theta, but minus r sine theta is just minus y, and r cosine theta is just x. Okay, so minus y x. This is just the velocity. This is just the velocity field for this is the velocity vector field for curves that are circles. Okay, so really what we see here is that the solution to this system of equations we kind of predict are going to be circles. And this is fine reasoning if you actually want to use this to find the characteristic equations, but I'm going to assume that you didn't know, that you didn't make that observation, because if you're just kind of doing things the way that we normally do things. Okay, so now with that aside, that's just kind of I hope an interesting geometric thing to think about. All right, so now we want to actually solve these systems of equations. So z of s, notice z dot doesn't involve anything other than x, or other than z, so it doesn't involve x and y. So I'm going to go ahead and solve that, because that one I can do pretty easily. Z of s is equal to f of x naught times e to the s. Times e to the s. Okay, So now let me think through how I can solve this system of differential equations. Well, I'm going to write it. I'm going to write it in matrix vector form. So I'm going to write x prime. So xy prime is equal to 0, minus 1, 1, 1, 0 times xy. And then this is the initial condition. Okay, so now I want to solve this system of differential equations. So that's going to take quite a bit. So I've got this over here. So I want to solve this system of differential equations. And remember, the first thing that I need to do here is I need to find the determinant. I need to find the eigenvalues and eigenvectors of this matrix. So I'm going to look at the determinant of 0 minus lambda minus 1, 1 minus lambda. This is equal to lambda squared plus 1. So lambda, we get two eigenvalues plus or minus I. If I set this equal to 0 and solve for lambda, those are the solutions. And remember, I'm just going to find, when I have a complex eigenvalue or a non-real eigenvalue, I'm going to find, I'm just going to take one of the solutions, one of the eigenvalues, let's say plus I, find the eigenvector associated to that, do the thing with the real and imaginary parts. So now I want to find the eigenvector associated to I. So in other words, I need to solve the equation minus I minus 1, 1 minus I times xy times the vector xy equals 0, 0. The solution is going to give me the eigenvectors. So notice that the top equation is equal to minus ix minus y is equal to 0, and the bottom equation is x minus iy is equal to 0. Observe that the top equation, the top equation is equal to minus I times the bottom equation. Okay, whenever we're finding eigenvectors, if we've done everything correctly, the two equations will be multiples of each other. Okay, so if I look at the top equation, so in other words, this is kind of, the bottom equation is kind of superfluous, or the top equation is superfluous. Okay, actually I'm going to use the bottom equation, because the bottom equation tells me that x is equal to I times y. Okay, so any vector, any multiple, any non-zero vector where the top coordinate is equal to I times the bottom coordinate, so any non-zero multiple of this vector is going to be an eigenvector associated to the eigenvalue 1. And so to find the general solution, we're going to look at the real and imaginary parts of e to the it times this vector I1. So we're getting the general solution first. So by Euler's formula, e to the it is cosine t plus I sine t. So that's how we split the exponential into real and imaginary parts. And for this one, we'll get, for the vector, we'll split this into real and imaginary parts. This is 0, 1 plus I times 1, 0. Okay? And now I want to split this whole thing into its real and imaginary parts. So what is this going to be equal to? Well, how do I get a real vector if I do cosine times the first vector or I sine times the second vector? If I do I sine times the second vector, I'm going to get minus sine t. I'm going to get minus sine t in the first component. In the bottom component, I'm going to get cosine t plus I. Well, how do I get an imaginary vector? If I do cosine t times this vector times the second vector, that's cosine t, or I sine t times the first vector, I'm going to get sine t. Okay, so the general solution then, is going to be, whoops, I forgot my constant. Well, I'll just write xy. X of t, y of t is equal to c1 minus sine t C1 minus, I don't know why this is having trouble with ins, sine t is there, cosine t, so that's C1 times the real part plus C2 times the imaginary part, cosine t, sine t. Okay, so this is the general solution. Now I need to actually figure out what these values of C1 and C2 are. So I'm going to have to insert a page here, it looks like. Okay, so I've got C1 minus sine t cosine t plus C2, I think that was cosine sine. Yeah, cosine sine. And I know that when I plug in t is equal to 0, I'm going to get x not 0. So in other words, I'm going to plug in t is equal to 0. I'm going to get 0 cosine t plus C2. Whoops. If I plug in t is equal to 0, cosine of t is just 1. So this is going to be 1. Plus C2, if I plug in t is equal to 0, this is 1, 0. Let me make this look more like a... And I know that this is equal to some x naught 0. Okay, so notice what's happening here. C1 times 0, so I just look at the top equation. The top equation says C2 is equal to x naught, and the bottom equation says C1 is equal to 0. Okay, so now if I go back to the previous one, C2 is equal to 1, C1 is equal to 0, so this part's going to go away. Or sorry, C2 is equal to x naught, C1 is equal to 0, so the particular solution, that part's going to go away, and the C2 is going to be x naught. Okay, so that is the solution to the to this initial value problem. So let me take those markings away so you can see them in. Okay. So now what this tells me is the solution to the characteristic equations, x of s, I think that's the one with cosine first, right? X of s is equal to x naught cosine t, and y of s is equal to y naught sine of t. Oh, sorry, sine of s. I think I'm using s over here, and I use t down here. Sorry about that. I just switched the variables. Sorry about that. But I'm not going to do this whole thing again. So basically, in this page, wherever I see an s, wherever you see an s, there should be a t. So wherever you see an s on this, or sorry, wherever you see a t on this page, there should be an s. Okay, sorry about that. So x of s is equal to x naught cosine s. Y of s is equal to y naught sine of s. So let me just pick a generic point here on the x-axis. Let's call this x naught. Okay, so what type of curve is this? Well, it's going to be a circle. The radius is going to be x naught. And when s is equal to 0, we're going to be on the x-axis here. And then, let's see, that's basically going to be like right here. And something like right here. So, wow. This is supposed to be a circle, but it's not great. Okay, so this is like a half circle. And when we start here, okay, so what exactly is going on with the method of characteristics here? Okay, it says that for a particular value of x naught, for this characteristic curve here, if this is AB, u of AB is just going to be f of x naught times e to the s. And e to the s, what is s? How do I relate s to what's going on here? S is just going to be this angle here. So S is just that angle. This is the angle S. And if I want to know what U is at any point on the curve, I just need to figure out what this S is, and Z of S is going to be equal to f of x naught times e to the s. Okay, now we actually, again, I want to actually write a formula like U of AB is equal to something, but looking at things geometrically is actually very helpful, and we'll see that more next week specifically. But this just says if I know what this point is here, so if I want a formula, but let's just say I'm given a point in the plane and I want to just know what the solution is along this curve right here, well then I can use this idea right here. U of AB is just going to be f of x naught times e to the s, where this is the angle here. Okay, and it's not clear yet why I need to stay in the right half of the plane. In other words, it's not clear yet why I can't go over to the left side of the plane. But as we start to figure out a formula for like y naught and s in terms of a and b, I think it will become more clear. Okay, so U of AB, so this is just a generic point. AB is a generic point. U of AB, sorry. This is x naught that I didn't, okay. U of AB, so for this point, U of AB, for this generic AB, U of AB is equal to Z of S, where again, S is that angle that I drew, and Z of S is equal to F of x naught e to the s. I can either think about this as being the angle that it's this being drawn, or kind of going s units along the curve in this way. Okay, so U of AB is equal to f of x naught e to the s. So now given an AB, I need to figure out what x naught and s are. Okay, well for x naught, that's not going to be so difficult. X naught is just the radius of the circle. So x naught is going to be like this distance from there to there, that's also x naught, because x naught is the radius of the circle. So x naught is equal to the square root of a squared plus b squared. So x naught is equal to the square root of a squared plus b squared. And what about s? Now, s is going to be a little bit trickier. And this is where we're going to see why we need to only look at the right half of the plane. So tangent of s is equal to b over a. Tangent of s is equal to b over a. So what this means is s is equal to arctan of b. Come on. S is equal to arctan of b over a. Now this formula works only when s goes from minus pi over 2 to pi over 2. Why is that? Because the arctan function, whenever we do trigonometric functions, we have to define whenever we want to look at inverse trigonometric functions, we have to define a branch of the actual trigonometric function. So we're only going to look at tangent going from minus pi over 2 to pi over 2. If we look outside of that, if we go from like minus pi over 2 to 3 pi over 2, well, the inverse is not going to be well defined because there's going to be multiple angles that have the same tangent. So this is why we need to say that we only are going to have tangent go from minus pi over 2 to pi over 2. We could have done something similar. We could have said y greater than 0 as well, and we could have done something similar, but that would have been a little more subtle. Okay, so as long as we're only looking at positive values of x, as long as we're only looking at positive values of x, we know s is going to be going from minus pi over 2 to pi over 2, and so the arctan function is well defined, and we can do everything that we need to do. So for this problem then, U of AB is equal to f of x naught. X naught is equal to the square root of a squared plus b squared, and then e to the s is equal to arctan of b over a. And so just switching to x and y, u of xy is equal to f of the square root of x squared plus y squared times e to the arctan of y over x. And that is the end of this problem. Okay, so that's it. This is the solution to the problem. I will let you guys actually show that this satisfies the PDE. But there's one other thing that I want to mention. So if I come back up here, if I forget about all of this method of characteristic stuff, or not forget all about it, but if I kind of forget all of this stuff here, and just sort of think about the solution as being z of s is equal to f of x naught e to the s, well, there are ways that I can continue it this way. Like it is possible to continue it this way, but I'm going to have to pick a different branch of the tangent function to continue it this way, and I'm going to have to pick a different branch of the tangent function to continue it this way. But notice there's going to be something very interesting that happens, because what's going to happen when I go around the solution this way, and I get to this point, when I go around the circle this way, and I get to this point right here, so this point is going to be x is equal to 0 and y is equal to minus x naught. So here's the problem. Here's the big problem that's going to happen. If I start at this point and travel counterclockwise, it's going to say that u of 0 minus x naught is equal to f of x naught times e to the s, where s is 3 pi over 2. However, if I start from here and go in this direction, it's going to say that this is equal to f of x naught e to the minus pi over 2. And so there's something weird that's happening right here, and this is why this is one of the reasons we need to make the assumption that we're only looking at the right half of the plane, and that's basically just so the circle doesn't come around and meet up with itself. Okay, the other issue is that if I were to open the domain, so it's still possible to solve this PDE if I just say look at the quadrants 4, 1, 2, and all of the third quadrant except for this line right here. If I were just to look at something like that, I can still solve the PDE. But notice that I couldn't specify the values of x along this. I couldn't specify the values of u along this part of the curve right here, because once I know, once I know u at this point, I can figure out what u is at the corresponding point over here just by following it around the circle over there. Okay, so this is a PDE with some interesting phenomenon, or with some interesting phenomena, and we'll talk a little bit more about that in the following slide, or in the following page.